to introduce the ESMVal tool, but from the point of view of a scientist. And so, yeah, firstly, like ESMVal tool, it's a software toolkit, and it's built to evaluate models of the Earth system. So what that means is that we should be able to look at the CMIP5, the CMIP6 datasets, as well as other things that are built in the same vein. So it's a versatile, flexible, and modular toolkit. It's built to work with standardized datasets, and the actual development is community-driven. So there's 12 core developers and more than 137 users at last count, not including your good selves. So the way that it's built is it uses quite a lot of sensible code development decisions, like code review, lots of unit and integration tests. All the design decisions are very transparent, and it's all publicly viewable on our GitHub page. And from my side, when I was a new user, I found that the development team were very friendly and accessible and quick to respond, and very helpful. So I can only say good things about them. It's built on using Python 3 and is PIP 8 compliant, which is just a code standard, and it's available on GitHub and fully open sourced. And it is easy to use, I promise. It may seem daunting at the beginning, but it is. So the kind of stuff you can do with it, these are just pictures from the ESMVal tool gallery page. So it kind of covers all sorts of different diagnostics of the Earth system. I must admit, I don't really know what all of these are, apart from the bottom left one, which I made, which is the Atlantic Meridional Overturning Current Circulation. Sorry, that's the strength of the North Atlantic AMOC. It's a multi-model comparison time series, but there's lots of different other kinds of data analyses, as you can see here. If you want to have a look, that's the link at the bottom right for all these different pictures. It's always a good place to start when you're just trying to see what you can do or trying to find something that's like what you want to do. So the documentation is on the GitHub page, and that's access to the code. And the read the docs page is a very useful one, as it includes our most up-to-date version of the documentation. It also includes an API that will go through ESMVal tool function by function. There's also currently 2 papers available about ESMVal tool version 2. There's a technical overview paper by Mattia Righi, and there is an extended set of large-scale diagnostics paper, which is by Veronica Eyring. It's in discussions at the moment, but I think we recently submitted the revised version of that. Some caveats for the code. V2 is published, but it is ongoing, and we are revising it regularly. There is an initial steep learning curve, but the documentation will help quite a lot nowadays, as will the code authors and the GitHub issues page. It is possible using ESMVal tool to combine recipe ingredients into something that's nonsensical. So you do have to be aware of what you're doing. All the model and input model and input observation datasets need to be Seymorized. So that's an important issue. Irregular grids may need to be regridded for some operations, especially things like comparing multiple models if they have a different grid. It's not built yet to monitor ongoing runs, so I'll explain what that means later. The sigma depth coordinates are not fully supported yet either. And there are surprisingly few generic plotting tools available. All the diagnostics and recipes are tailored to do a specific thing. And there's nothing like, I just want to have a look at this. They're all very specific tools. So this slide here shows the sort of a schematic of how ESMVal tool works. But as a scientific user, you only really need to know the 4 main things. So they are the preprocessors. So what these are is individual functions that perform an operator on the data. So whether it's load or save it, or regrid, or apply a mask, or take an average in the spatial direction, or take an average in the temporal direction. So those are the preprocessors. The diagnostics, those are scripts that you use to evaluate the process data. So that can be making plots, or it could be processing it further and saving it as NetCDFs, or calculating statistics and outputting it as a table, or even producing a web diagnostic or something like that. The recipe is the global set of the set of instructions that you want to apply, and the user configuration, these are the files that like the input settings of ESMValTool. But the analogy that I like to use to explain it is Lego. So the preprocessors are individual modules that all stick together and can be combined in any way that you want to produce your final product. So like Lego bricks. The recipe is the instructions that tell you the order and what you want to do. The user configurations are the information that tells ESMValTool where you keep all of the parts, where they all are, and how they all, where to find things. And the diagnostics is playing with your Lego bricks after you've built them. So that's kind of the way that I tend to think of it, and hopefully that will help you as well. And I'm going to refer to these pictures regularly throughout this talk. So the preprocessors, these are, which you guys know a little bit about. So it'll take an iris cube, some arguments, and then apply an operator to the cube and return another cube. So this is load and save, fix the data set, apply CF compliance, adjust the strictness of the CF compliance, extract the time, perform an annual average, regrid, extract a specific region or a transect, do depth integration or a zonal mean, then apply a mask thresholds and do multi-model statistics. So things like the median of several models. And there's a full list of all the processes in the API on the Preprocessors page. So as a sort of a thought experiment of how a preprocessor would work, so say we start with our full 3D plus time data set, something like 3D ocean temperature time series. We say we want to extract the surface layer, just take the top of it. Then we want to extract the equatorial region, and then we take the area weighted average of that data set. So it goes from a full 3D plus time data set down to a one-dimensional, time-dimensional data set. So that would be a fairly standard thing that people would want to do quite regularly. And the output is, one-dimensional time. So as an example, this is what that would look like in ESMValTool. So just a quick comment. This first line here, the custom order is true, means that the order that you put the preprocessors in your recipe will be the order that these operations are performed. And there is a default order, but if you include the custom order, it enforces this, the order that you write it down in. Okay, so the first command is extract the levels. So the level is a depth of 0, so 0 meters. And the scheme is the linear, horizontal, extrapolate along the vertical. It's a standard operation. Extracting a region is the next one, where we look at the latitude of -10 to +10. And then the area statistics operator is the third one, and that applies the mean and requires the area weighting of the cell area. So you need to tell ESMValTool about the cell, the weighting for things like area averages and volume averages. So the next key thing to look at here is the recipe. So we just saw an example of what a recipe looks like. And this tells ESMValTool what model to use, what project data set to use, which scenario, ensemble members, time resolution, time range, which preprocessors to apply, the order to apply them, the arguments that you give the preprocessors. Tells you which diagnostic to load, which variable, where the path to the diagnostic file is, the script, sorry. And it tells you how to link it all. So that's what contains in the recipe. And now I'm just going to go through, well, I'm going to go through one in a moment. But before, the user config is at the global settings. So this tells from things like your preferred output format, whether you want your images saved as a PDF or a PNG file, that kind of stuff. Whether you should save intermediary cubes. Now this will fill up your disk space quite quickly if you're not careful. but it's very useful for debugging if you're working your way through the pre-processing stages. This tells ESMValTool where your model data file is and where you want to put your output. Oh yeah, a useful tip, you can have more than one user config file. So you could have a sort of a production one that has everything in PDFs and all the debugging flags set to minimum. And then you could have like a debugging one, which is, you know, just a quick image format like a PNG or something, and as much debugging information you need. And so as you choose it at runtime, you just tell it which one you want. Okay, so this is a user config file. The crucial stuff that I found is log level, the output file type, the output directory, and the flag save intermediary files. The actual path to the data files are set in the config developer.yml file, which is in the path ESMValCore, ESMValCore. And so these are combined with the root path in your user config to produce the path on disk that ESMValTool will look for the data. It may seem complicated, but if you're just using Jasmine, then it's a very simple edit to your global file, and ESMValTool will know exactly where to find everything. If you were working on a system that's not listed there, like your home computer, for instance, then that becomes a bit more complicated. But I don't think anybody's going to be copying vast amounts of CMIP6 data to their desktop anytime soon, at least. I hope not. Yeah. Oh, yeah. So the big thing to notice here is you must edit the default user config file to run ESMValTool on Jasmine. The default one is not set up for Jasmine, so you must edit it before you use it. Now, RunGenie will help us do that later, and I believe it might even be in the instructions how to do that. Okay, so moving on, Diagnostics. This is playing with the datasets once you've produced them. So this is plots, statistics, processing the CDFs, combining them in interesting statistical ways. So this can be done in Python, NCL, R, or Julia. There's all ready to go ones, but there's no sort of native, generic, or smart diagnostics. They're all very much tailored to a specific purpose. So you need to be careful. You also need to know what each diagnostic does and the required format of the input files. And if it's not there, you may get the chance to make your own one, which is always fun. Okay, so now I'm going to go through a recipe. So this is the recipe Ocean Quad Map. It's in the ESMValTool recipes folder. You're welcome to look it up on GitHub or just follow with the slides now. So the first section of every recipe is the documentation section. I mean, it's pretty obvious what it is. It's the author, the maintainer, a reference to what it does, information about the project, and a description of what it is. Oh, by the way, yes, some parts of this example might be slightly out of date, as there's been some subtle changes to ESMValTool since I wrote this talk. Okay, so the next section. Okay, this should have been in the previous slide. Looks like the order's all wrong. Okay, so the parts of a recipe, the documentation, which we talked about already, the datasets information, the diagnostic section. It's in YAML format, YML, so indentation matters in this format. Preprocessors, they are necessary. Well, they're not always necessary, it's what I mean. It's helpful if you want to apply operations, but if, for instance, as in this case, there is no operation needed to the dataset, you don't actually have to have them. Okay, so in this recipe, we've got documentation, the datasets here. If you look on the left-hand side of this slide, you'll see a list of datasets. These are all CMIP5 datasets. It's experiment is historical. The ensemble member is R1, I1, P1, and it goes from the year 1900 to 2004. That is how a dataset is provided. It's fairly straightforward. CMIP6 datasets also require the grid, which will be GN for sort of native grid, or GR for regridded grid. There's a couple other ones, but those are the two main ones to know about. And then you can see at the bottom of this example, the diagnostics. It goes, we give it a description, we give it the variable MFO, which is the seawater transport across the line. And it's the OMON-MIP, which is the monthly ocean datasets. And then it's passed to the diagnostic time series script, and the argument here is moving average set to 6 years. So that is specific. The moving average argument is specific to the Ocean Diagnostic Time Series Python script. Each script will have its own arguments to give them in the diagnostic section here. So it's worth looking to see what arguments are expected by the script if you're writing your own RISP. Okay, so to run it, this is the command. Once you've set up everything and you've got your con space working, it's ESMValTool -C, and you provide your config user file, and then the risp.yml file. Once it runs, it will produce a new folder for every run, and the location of the folder is determined in your config user file. So it'll be something like this one here. Global Ocean is where I keep my stuff. RISP, Ocean, AMOC, then a date and a time. And that's supposed to be 2 lines, so I'm sorry about that. And with the $sign. Anyway, you'll see. Inside that folder, there will be 4 further folders. There'll be the preproc folder, and this will contain all the preprocessed CDF files. There'll be the run directory, so that's the log, a copy of the recipe, the settings and the metadata file. There'll be a work directory, which is where the work directory is where your diagnostics can be saved, your diagnostic output in its CDF files, basically. But that's up to the diagnostic to do that. And then the plots folder will be where all your files should be saved. Okay, so running ESMValTool, it will run the preprocessors first, and when they've all completed, it will then pass that data on to the diagnostics. Now, if you are developing a diagnostic, you can run the diagnostics individually after the fact. Say, for instance, you are working on your diagnostic Python script, and you put in a typo, then you can just rerun that diagnostic, so you don't have to rerun the preprocessor every time, which saves quite a bit of computational time, depending on what you're doing. So at the end of the ESMVal, like on-screen terminal output, there'll be this line that says something like, to rerun this diagnostic, run, and then there'll be a command that looks like this, path to the script, and a path to the settings. And yeah, it's really, really useful. And there's 2 flags you can add at the end. F means you delete everything and remake the output plots. Or I means you just overwrite previous plots. So bear in mind, look out for that command, very handy. Okay, so I'm just going to show now a couple ocean diagnostics tools that we've been working on. They are fairly generic as far as they can be. And they're in the master branch now under Diagnostic Scripts Ocean. So they can do things like time series, profiles, maps, transects, models versus observations, and extents. I'm just going to show a couple of them now real quick though. Some of them are written in a fairly generic way, and so they might actually be useful to investigate atmospheric stuff or land surface if used cautiously. So time series, as a basic example, they were looking at the HADGEM2ES in the historical, in the ocean, the sea surface temperature, and we're looking at the years 1960 to 2004, and the equatorial region again, and the surface average. And the diagnostic time series, it will produce a plot that looks like this one. So you can almost set this up yourself and have a play with it if you wanted to. With this example recipe, and this, if you added sets, it would also automatically produce a multi-model comparison like this one. Similarly, this is a map. You just need to provide a cube with a latitude and longitude. And there's a transect for a latitude by longitude or depth by longitude. And yeah, okay. Yeah, so basically ESMValTool was built to evaluate CVIPS models, and it's optimized to be as flexible as possible. It's sensibly built. There's lots of rational design decisions, and it's built in a modular fashion. But there's lots of diagnostics available as well as a starting point for doing your own work. And there's lots and lots of CMIP6, UK ESM1, and now available on Jasmine. So thanks.
All right, so what I'm gonna do now, I'm gonna give you guys a practical example of how to run ESMValTool on CMIP6 data. I am logged in onto Jasmine. I managed to get onto Jasmine Sci5, as you can see in the login prompt. I am also in the ESMValTool virtual environment because you have this ESMValTool in parentheses right before the login prompt. So this means that I have installed the ESMValTool from source, and I checked out the Git ball. I created an Anaconda virtual environment called ESMValTool, and when that happened, Anaconda or Miniconda, Conda, it's the executable, installed all the dependencies needed by ESMValTool and ESMValCore. ESMValCore is actually one of the dependencies of ESMValTool, and it's the module, as Lee described before, is the module that does all the heavy lifting computations, all the pre-processing. And then I've installed the ESMValTool via pip or Python setup.py install, whatever the option. And we recommend pip because it's much more flexible in terms of the dependencies that get installed while the installation process is happening. So now I have ESMValTool, and I can actually check this by minus help. Just running the help splasher, and I got my help menu here. It tells you, well, it gives you a logo of ESMValTool, very 80s looking logo. It tells you who's in the core development team and contacts in case you get stuck. Obviously, Ranjini and Lee are the main contacts in this case. And you have your command line options in here, which obviously starts with help, version. We'll check out the version in a bit. -C config file. This is required. It's the user configuration file that you pass to the tool to know where the data is, as Lee explained before. You know, all the what data sets you're using and all the jazz. -S Cinda download, in case you're not running ESMValTool on a node that has data, whether it be CMIP or ops data, you can prompt it to download data via Cinda, and that will be only CMIP data because Cinda cannot download any ops or ANA for MIPS or ops for MIPS, stuff like that. Then you can limit your data sets. You can limit your ears. You can use skip non-existent, which is a convenient option to skip the data that's not being found. So if you're running with a large number of data sets and a few of them are not found, you can tell the tool skip the ones that are not found and don't throw out an error. Just go over and work with what data is available. Diagnostics. This is useful when you run, when you rerun, or you have a massive recipe with a whole bunch of diagnostics and you just want to run a certain select group of the diagnostics, not all of them. And check level. This is very useful because you determine, as a user, you determine the level of strictness in terms of the CMOR formatting of the data. So data that's on ESGF is usually CMOR compliant, and it's CMOR compliant to the highest standards. Well, it's supposed to be. A lot of the times you find out that there's a whole bunch of CMOR formatting irregularities with ESGF data. So you can actually throttle the level of CMOR compliance using this command line option and given different levels from what are the levels, relaxed or medium level, or be very stringent about it. This comes in hand also when you work with data, the CMIP data or ops data that is not necessarily on ESGF, and it is, you know, like Primavera data used to be, now it's on ESGF. But before that, it was kind of like in-house developed and outputted data that was not necessarily super CMOR standards, but it was, you really need to run the evaluation tool on it, so you can say, well, don't care that much about the CMOR standards. Right. So we can actually have a look at the version. And version is, if Jasmine permits, it's 2.00b9. That means we are not at stable version 2.0 just yet, but we are, well, we're B9 iterations into the process. So hopefully in a few weeks, we'll be able to release version 2 stable and actually come up with a plan on how to release version 2.01 and further on periodic releases. This is what we're going to be discussing in the core development team. Anyway, so now I want to run ESMValTool. And what I'm gonna need two files, as Lee described before. One of them is the configuration file, and I'm gonna use a configuration file for CMIP6, and I'll run you guys through it briefly. And I have one that is actually CMIP6 specific. So if we go to the top of the file, there are a whole bunch of options that, so this is a YAML file. That means it usually goes by the general rule that is a massive nested dictionary. So it's got key, which is in green, and value, which is either in white if it's a string, or in red if it's a Boolean operator. So the key value pair defines your the way you input your data in the configuration file. So we have a whole bunch of options here. These are described in the documentation, and also they have commented out doc strings in here. A few of them are important, and I'm going to go over them now. The log level, that's info. That means when you run the tool, you get the basic information splashed to the screen, outputted to the screen. You don't get what would be the debug log level, and that would be a lot of information. You know, in case something goes awry in your run, you want to get as much information as possible, so you actually figure out where it went bad. That's output directory, as Lee told you before. This is the directory where everything is going to be written to during the runtime, and it's called Lee because I was running something for Lee some time ago. Max parallel tasks. This is a useful option for the user to select the number of threads that the tool can run on. So if you specify, if you have a lot of computations to be done, it'd be nice if you selected, you know, a few more threads than just one, because that means you'll get the process will get spawned on those threads. You got to be careful here, because if you select too many, say if you want 200, that might actually be possible in terms of the hardware. So things will get very slow because it'll try to create virtual threads, and that's gonna take a lot of memory. So it's basically gonna stop. But you know, it's 8 is a good number, or 6. Data locations. This is where you specify where your data lives, and this is done via the root path option. And there's a bunch of key value pairs in here. So we have CMIP6. This is where the CMIP6 data. This is the root path where CMIP6 data lives on Jasmine. You can specify a private repository, as in like your own repository where the data lives. And I was running a whole bunch of autosys experimental stuff in here, so I was using my own data. And then this is the ops data and ops6, which are equivalent, but ops6 is more modern, and this is where the ops data lives on Jasmine. It's in the ESMVal group workspace, Jasmine 4. It's a fairly large directory containing a whole bunch of tier 1 to 3 ops data. Well, ops for MIPS is tier 1. And then tier 2 and 3 is proper ops or ops6. We have a lot of ERA interim there and a whole bunch of other ones as well. But specifically ERA interim is there. We don't have much ERA 5. Actually, we barely have any ERA 5 there, but this thing is growing, constantly growing. So call it kind of like a BDC equivalent for ops data. And then you will have to pass it the DRS, which is the standard excuse me, which is the standard way in which the paths are built on different machines. So I'll tell you more about this once we actually get to the recipe. But in this case, the DRS is BEDC. If it was if you'd run the other tool on DKRZ, it would be called DKRZ. It would be on ETHZ, it would be ETHZ, because they store data pretty much in the same way everywhere, but there's a little bit tiny bit of the differences in terms of where the files live. Anyway, that's about it for the configuration file, and we'll have a look at the second most important file that you need to use while you want to run. That will be the recipe. And we're going to use a recipe which does a very basic model intercomparison. So you basically have two models and you want to compare one against each other. One of them, you can call it the control, the other one will be the experiment model. So, and we're going to use the validation for CMIP6. This is what the how the recipe looks like. It's divided into main sections. Again, it's a YAML file that this time is a little bit more complicated than the configuration file, because this time around you have it is the proper nested dictionary, because you have main sections, you have subsections, and then you have a whole bunch of key values for each of these subsections. Anyway, we'll start from the beginning. The first section is the documentation, where you have a short description of what the recipe does. So this one uses a control and experiment data set, standard comparison between two models, doing a whole bunch of 2D lat-lon and zonal and meridional means. Fairly basic stuff. Then you have the authors and the maintainers. These are, so the documentation and the author and maintainer are used, for bookkeeping and for provenance checking, because the author has to be a registered author with ESMValTool. Then the second main section is the data sets. The data sets come as, it's a list of dictionaries, and each of the dictionary contains data set name, project, MIP, and Johnny was asking why OMON is a MIP. This is a MIP because this is what the MIP tables from the Seymour guys are using. And a whole bunch of other data-specific descriptors, the experiment, the ensemble, the grid, because it's CMIP6 data that regridded grid or native grid. That's what GR and GN stand for. And then the time boundaries, the start here and end here. These data sets, well, you can put a whole bunch of them in here, so you can ask for as many as you want, and they don't necessarily have to be just CMIP data. They can be any other OBS, ANA from MIPS, OBS from MIPS, and so on and so on. Yeah, that's correct, Emma. Cheers. And then the third section is the diagnostics. And you give it a name here and a very short description. And there's your variables. There's a variable. This is a list. Could be a whole bunch of variables. And you item them by the short name. And you give under each variable you give a whole bunch. You can give a whole bunch of instructions. In this case, the preprocessor that I'm going to be running over this variable is called ppred, which is I actually skipped the preprocessors. Yeah, sorry. In this case, is the only preprocessor that I'm running. I'll come back to the preprocessors. And you can pass a whole bunch of additional data sets that are not part of the datasets section. These are variable-specific data sets, so you don't have to use the global datasets key there, because they will be used only for this particular diagnostic here. And then there's the scripts, and that's the diagnostic scripts that will basically run your science bit. And I have 1 lat lon, 2 zonal mean, 3 meridional mean. I have three different diagnostics that I'm going to be running, and each diagnostic accepts any given number of arguments. Again, key value pairs that the user wants to give, knowing that the diagnostic itself knows how to recognize these arguments and knows what to do with them. So you, as a diagnostic developer, you can say, so I want my diagnostic to run the validation.py script, and I want that script to input the CMIP era, CMIP 6, and I want to define my control model this and experimental model that, and I want to use these observational data sets in form of a list. And then the diagnostic will know that these are important things, and it will parse them, and it will extract the information and use it. Now, the preprocessors, this is the first thing that I managed to wisely skip it. This is the first thing that that's been run before running the diagnostic. So in this case, preprocessors is a list of multiple preprocessors. If you want to run these on your different preprocessors for different diagnostics, and they're identified by the name, and then is a list of preprocessor steps or modules. In this case, the only step that I'm running is the regrid, and I'm regridding on a 1x1 degree grid, and I want to be using the linear interpolation scheme for regridding. These could include a whole bunch of other things that these are the Lego blocks that Lee was telling you about in his presentation, and they include all sorts of masking and volume area statistics, time operations, multimodal statistics, and so on. So with this in hand, then what we'll be doing, we'll just be running this. And you do it ESMValTool -c config-user CMIP 6, not 5. Recipe validation. And now it's running. And I will try to tell you. So I'm running with log level info, I don't want to splash a whole bunch of information to the screen, but it's still outputting enough information so that you know what stage of the run is at the moment. So it outputs the standard information, core developers and so on. It tells you I'm using the config file, this one that I'm actually using now. Then it tells you it's writing the log files too. So it's created this directory, Lee, and it's got recipe validation CMIP6, and it's identified by a datetime string. And this is unique because when you run multiple instances of this diagnostics, you want to rerun, something went wrong, or you want to tweak a little bit your parameters, run parameters and rerun, it will create a new directory with a different datetime tag here, so that it doesn't overwrite the previous run. And then that tells you a bunch of standard information, what recipe I'm using. I'm using the recipe which is stored locally in here, run directory, which is this one, and it's run, work there, preprocessing there. So it creates this directory structure where the different stages of the run produce files, and they store them in different places. And then it tells you it's running tasks using at most 2 processes. That means it's running on two threads. It's creating the tasks. And it's looking for data now. So it's telling you it's using data from this location. And now we can actually talk a little bit about the DRS, because you can see where the file, the data file that the diagnostic needs is stored on the CEDA, whatever used to be called before BADC, the CEDA Jasmine ESGF node. So the DRS is the standard path where the standard path descriptor where the data is stored, in this case in BADC. So that is composed of the root path that you gave it in your configuration file, and then it's the model and data specific rest of the path, which ends with the actual file. So it's basically institution, model, experiment, ensemble, MIP, name of the variable, name of the grid, the version of the data. In this case is latest, but latest is always a soft link to the actual latest data. There's a whole bunch of previous versions of the data stored in here, but Jasmine always links to the latest version. And then it's the name of the file. The name of the file is also a standard operator. It's part of the DRS. And then it's looking for the observational data sets, which are stored in the ESMVal ops data v2, and it's grabbing a lot of them because I needed, how many years did I ask? 2000. I asked for 20 years, and these are stored in yearly files. And then it goes on to creating diagnostic task for validation. So that's the diagnostic tasks. While this is running, it's running the preprocessor as well. So remember we had the regridding to be done. Before regridding, it does a whole bunch of other steps of the preprocessor that are default. And they're under the hood because you don't need to know about those things. So it's selecting it's checking the validity of the data against CMOR standards, and because you didn't actually ask for any specific CMOR level when you ran the command, it does the the default CMOR checks, which are the most stringent ones. It selects the time because you want it in between 1980 and 2000. So it grabbed, it found the data, but then it needs to time gate, and concatenates the files because these ERA files, ERA interim files, they came in different chunks. So it puts those together, and then it runs the regrading. And then after that, it says, well, I don't have to run any more pre-processing steps, so I'm just going to go ahead and link up with the diagnostic script, which is the Python script. That could be R, that could be NCL, that could be Julia as well. So it's basically using a sub-process call to the actual diagnostic runner. And it's running the diagnostic. So running command. This is the command to run the diagnostic. And then it's writing the output and the logs and the plots to these directories. And then goes ahead and runs the other diagnostics. Remember, we had 3 scripts to run. So the lat-lon, zonal, and meridional diagnostics. And at the end, it tells you it finished successfully. So now we can actually have a quick look at the actual output. So it's in Lee. So I ran this twice. Ran it as a trial run at 10:21, and then I ran the actual run at 10:54. So and you see it didn't overwrite my previous run. It outputted in a separate directory. So now I want to have a look at my latest one, which is that did not account for the summertime change, actually, but that's fine. So we have these output directories, which are plots, pre-processing, run, and work. What we have in plots we have 3 directories with plots because we ran 3 diagnostics. Well, 3 scripts. Sorry, 3 calls to the diagnostic. So there's the lat-lon, the meridional, and the zonal means. So each of these contain plots. Let's see what's in lat-lon. As all time and then by season. So we have a bunch of plots in here. Unfortunately, I can't open the plots because I'm sharing only the terminal window. So that will pop up in a different window. But then that's fine. I mean, it's just you know that those are colorful plots, and they contain science and stuff. So these are the plots. Then we can have a look at the other directories, which are plots preproc. Let's have a look at preproc. In preproc, we have subdirectories labeled by the name of the diagnostic and the variable that was run. And we have only one variable, that was task. And in task, we have the output from the pre-processing. So we have the 2 models, UKSM and IPSL. So that's what the tool did. It grabbed the data, it ran all those under the hood pre-processing steps that I told you about, and it ran the regrading. And right before the diagnostic started, it outputted the result of the pre-processing module in the shape of an SCDF file. So it did all those things on the data, and now it says, I'm going to run the diagnostic, but before I do that, I'm going to write these files to disk, because these files are actually going to be used by the diagnostic. And it also writes, well, and the ops data as well, sorry. So the 2 CMIP models, CMIP6 models, and the ops data. And it also writes a metadata file. We can actually have a look at that one. And there's 50 metadata. So this is, in summary, what the what the operations were before the diagnostic and directives for the diagnostic. So it tells the diagnostic that I have this file name here, which is the preprocessed data file with these parameters: frequency, grid, institute, blah, 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 the project on all these things. And the variable is here. And then I also have this file here and so on. So this is the information file that is used by the diagnostic. So it's kind of like cookbook for the diagnostic to know what's being ingested in the diagnostic. And it's program agnostic, so it's basically a nested dictionary that can be used by not only by Python diagnostics but also R and Julia and NCL. So if you put your information in this way, then these diagnostics, whatever the programming language they're written in, they will be able to read and find actual data and with those parameters. And then we have run. Let's see what's in run. In run, we have a bunch of auxiliary files. Makes a copy of the recipe, and then it writes the log, what you saw on the screen. So that would be the std out, and it's actually written to file, and it also writes the debug log file. So we can actually have a look at this one. See, that's a vim. Okay, that's good. Main log debug. So this is your debug that you didn't want to splash the screen in debug mode, but you will have it anyway stored in your. And you see there's a lot more information in here. It's telling you all the ins and outs and what the operations, the under the hood operations are done. It's got when fixing the data, for instance, because this is the step that you didn't specify part of your pre-processing, but it's done anyway. This is the correcting for the CMOR standards of the data, and the fixed data is done using with check level, which is default because you didn't specify anything. A command line time, and then all these CMOR specific parameters, the frequency of the data, the MIP, the project, and so on and so on. And it tells you, oh, I want to fix the data, I want to output here, and so on. So this is very useful, but it's probably more useful if you're more of an advanced user than right at the beginning. Anyway, so it also gives you a usage, resource usage bits of information. So this is a nifty tool that outputs the run times at periodic time steps with periodic time steps, and tells you how much CPU it used and how much memory actual and percentage of the available memory on the node. So we can have a look that we haven't actually gone more than, oh, that's a lot of numbers. So let's see. We haven't got more than 0.6% of the available memory on Sci-Fi. So that's pretty bad. Pretty okay. That's pretty okay, not too bad. If you run with multimodal operations, then you're gonna, chuck in a whole bunch of data, and that has to be stored in memory. And that's you're gonna see quite a bit of memory being used. Yeah, so that's pretty much it. I mean, I told you guys about the config file, I told you guys about the recipe practically, and then we ran an example, and you'll see, you saw what's actually doing and how's outputting the data. And so I think probably best thing would be for you to run these things yourselves and see how they work.
Okay, thanks, Huy.